Alright, and now we're going to take it home. So we figured out that we had an equilibrium constant equal to Geiger's number equal to the standard molar partition function of component of the transition state C divided by that of A, that of B, and E0 over RT. Alright. And so then the question is, how do we construct these partition functions? And there's going to be one tricky part, and that's how to deal with the vibration that actually converts this transition state to the products. Now this one is thought to be a low energy one. So I always call this the magic vibration, and so the vibrational temperature for this particular vibration is normally going to be pretty small. So you can expect the partition function for that particular vibration and that one only to be the classic amount, which is just kT over h nu. So the partition function, the molar partition function for our transition state C can be said to be equal kT over h nu times this quantity Kc over bar, where Kc over bar is the rest of the partition function, including the translational component, the rotational component, and the other 3n minus 5 or 4, depending on linearity, vibrations. So with that definition, we can now actually fill in our equilibrium constant K double dagger. Cheat first and say that's equal to kT over h nu times big K over bar. And big K over bar is going to be equal to RT times standard P times the rest of the partition function. So Na C double dagger QA standard QB standard. Alright. One thing to note. This actually needs to be the true vibrational frequency, or it should be in hertz. And so here we have K with everything except the vibrational component in there. And if we take this into account, let's go back up top here now. So we defined the overall rate constant K2 as the product of K double dagger and K dagger. And so we can now equate that to the transmission coefficient kappa times that frequency of reaction, times the rate of reaction, I'm sorry, and times the factor kT over h nu for the partition function of that one vibration, times our over bar equilibrium constant, which we can now equal to as kappa times kT over h times K bar. And this is the as promised force cavalcade of Ks. But if you think about it, there's a lot buried in here, that this is the prediction of a kinetic, in this case a second order rate constant, strictly from microscopic principles, because buried in these equilibrium constants is a partition function that has in it molar masses, it has vibrational frequencies, it has moments of inertia, which influence the rotational levels, and just from knowing the structures of the reactants and the transition state, you can determine the rate constant of that process, which is fairly impressive, even if it is fairly unimpressive or unimaginative in its use of letters, because, again, told you, this is a lot of Ks. Now, and this is called the eyrin equation, so I will let that sink in. And the key is, in this case, accurate construction of the partition functions. So the problem, if you wanted to actually get a number for this, is by its nature, these transition states are transitory. They don't ever have very high concentrations, so their structures might not be known particularly well. But you can still do pretty, so in the past couple decades, ultra-fast spectroscopic techniques have actually observed directly some of them, not a lot, but some. And using things like gains, some theoretical calculations, you can get a pretty good idea. But even without that, you can make some reasonably good educated guesses for what the parameters of that transition state might be. And that can get you pretty far. And what a lot of people did is if they made some educated guesses and got a number that did not match a known experiment at all, and then they would probably refine their guess as to the geometry of the transition state. Now, just like the equilibrium constants, so I'll erase this here, getting these right all the way through is easier said than done, because a lot of work goes into the calculation of those partition functions. And so I would highly, highly, highly recommend that you try an example. There is one posted on the Moodle page for a real reaction, and I would highly advise you either try to do it or at least follow it along and take a look at it. And that's it. Out.